So this is our oscilloscope. It's a B&K 2530. It's a digital oscilloscope. We have some analog scopes back here, but digital, and you can actually see the digital, the A to D converter if you look real close. So it's two channel. So we have the ability to look at two things at the same time. Of course, we can see that this is definitely a half-wave rectifier, I mean full-wave rectifier. So this is the last one that we looked at. Now, the controls that we're going to be dealing with this semester is we're going to be dealing with these two guys right here. These are called your vertical controls. These are your volts per division. So this determines how big the waveform you're displaying on the screen is. Right now I'm looking at channel 1. So that's the scope probe right here. So they're labeled channel 1 and then channel 2. The display for channel 1 is yellow and the display for channel 2 is blue. So they even color coded over here around the knob. This is our position control. So we can put it into, like in the upper quadrant, one signal in the upper quadrant, and put the other one in the bottom. So we're trying to look at two things at the same time. This shows you where your actually zero reference is. So I know we're looking at DC, so that means if I set that one, if I set channel 1 to 0, so this is showing you your zero reference. So what we need to do is, if we're looking at DC, instead of wasting all this space down here, then what we do you to do is we try to move it down towards the bottom. Then what we can do is we may be able to put our volts per division. And now your scope is the most accurate. So the bigger you can make it and still keep it on the screen, the more accurate your scope is. I think the analogy I use is spit on it, right? So they spread that thing out. And also, this is our time per division. So by the way, I can turn this menu off. And this is the time per division. So we call this the horizontal control. What we want to do is we turn this. So as we speed up the trace, it's going to make it bigger. If we slow it down, it's going to put it close together. That makes sense? And then what we can do is we can read our scales down here. So these are the major scales, these big lines right here. Let me see if I can turn that up. So right there. Which one this is better? It looks like I haven't turned all the way up. Well, I could, but if you do, you'll lose it. You might lose it. Yeah, we got 2 free seats up here, right? Yes. So I think that's probably the best I can do. I got a little tilt on my camera mount. I did. Okay. I got the boom on so long. So now we can mix, so your scope, let's put it back, let me put it on the AC side. Now this is isolated. We need to really make sure we run that up. So this is the AC. So if I'm looking at AC, I want it to be set in the center. And I'm looking at channel 1. I'm going to put my zero reference back up here. Okay, so now you can see, now I need to see one cycle. That's what we're shooting for, is one cycle. So I'm going to slow my scope down. And then that's my AC waveform. So if you're looking at AC, then you want to set your zero reference right in the center. if you're looking at DC, then you want to shift it either up or down to get the as much display as you can. And this, some people will be on DC and they'll try to use this whole quadrant right there, and they're wasting all that space down there, or vice versa for a positive person. Okay, so we can measure, we have it on 2.5 milliseconds per major division. So this is the best I can do, because if I go here, I'm putting too many. If I go here, I don't see one cycle, right? See that? So this is the best I can do. Now, if we want to measure time, what we would do is we would cross it, either going positive or negative, don't make any difference. We're going to cross it on one of these vertical lines. So I want it to cross it. So this is the brightest we can make these symbols. So right now, so what I would do, this is the horizontal position, and that's the way it's labeled. So you see, if I can move this, the whole waveform moves. See that? If I move this, it goes back the other way. And what we're trying to do is figure out, measure time. I want to make this cross at one of the vertical lines. So we measure time this way, and we measure volts up and down. Time is left to right, volts is up and down. So right now, I would come over here, and put it on a crossing line. 2.5 milliseconds per division. Okay. If I count in ones, that means each one of these minor divisions is going to be worth a 0.2. We got 5 divisions between a whole number. Everybody understand that? So I would start right here. I'd say 1, 2, and we're going down on this one, so we're going to count to the time. It goes right there. So I'd say what? I'd say 1, 2, 3, 4, 5, 6.23.246. Notice I'm counting twos, right? 1, 2, 3, 4, 5, 6.246.
So 6.6?
Okay. And we would multiply that by 2.5 milli. In fact, you know your answer is going to be in milli, so you can just multiply it by 2.5 and just say milli, right? You understand that? Should be around 16.6 milli. Should be around. So this is 60 cycles. Now, if you take the reciprocal of that, that'll give you the frequency. So that's 60 hertz. So this is Alabama power, which is what we should expect. So that's 60 hertz. Now, the voltage we're looking at, when we measure voltage, we measure up from the bottom toward the top. Well, the problem is, I'm in the center of this one, but we don't have to do that. We're trying to measure voltage. I have the ability to put that sucker anywhere I want to. So I'm going to come over here and I'm going to shift this up until this trough is online. That makes sense? And then you can see the graticals are a lot better in the center. So what I use is I usually just move it over like that. You see what I did? And I'm going to measure from here to there. So this is, we got this set on 5 volts per division. So instead, we could do it this way. So I could go 1, 2, 3. Now it's 5 volts per division. If it's 5 volts per division, that means now each minor division is going to be worth 1 volt. Yeah. So if we count in ones, then each minor division is going to be worth 2, right? You understand? So I can go 1, 2, 3, 4, 5, 6.123 divisions.
That's 6.3? 1, 2, 3, 4, 5, 6. Yeah, 6.3.
It's 6.3. Then we can multiply that by 5. That's the volt per division. Or, since 5 is so easy, Does everybody know how to count five? I can go what? 5, 10, 15, 20, 25, 30, 31, 2, 3. So it's real easy to count. In fact, it's easy to count in one. The major range of most oscilloscopes are ranges of 1, which means if it's a 1, each minor resistance would be worth 0.2. 2s, which means each minor division would be worth 0.4. And then 5s, which means minor division would be worth 1. So after a while, everybody can count in 1s, everybody can count in 2s, 2, 4, 6, 8. Everybody can count in 5s. So after a while, you don't multiply. Normally, the way they teach it is to count the number of divisions and then multiply it by your votes per division. But most of the time I won't do that. I'll say 5, 10, 15, 20, or say 2, 4, 6, 8, or I'll say 1, 2, 3, 4. And then I'd count the divisions as 0.2, 0.3, if y'all understand that. So scopes are set up. These are kind of weird because it has a 2.5 division, but it's a digital scope. But if you ever look at an analog scope, 1, 2s, and 5. So you'd have 50 votes. If it's 50 votes per division, then each minor division would be worth 10 votes, right? So most of the time you can read this thing up. So here's the speed. Now let's come over here and look at our output. So this is the output. Now this one we can't look at the input and the output at the same time. What you have to understand, guys, is that black lead on an oscilloscope is ground. So you cannot probe within the circuit. You have to make all your measurements relative to the circuit ground, or circuit common. A while ago I was able to move it because this transformer is not grounded. If I was to put the ground where I measured AC, then I couldn't put my ground on the other side of my resistance. So it's not a meter. A scope is not a meter. So on a meter, if somebody calls this ground, you need to correct them. This is not ground. This is common to the meter. This has nothing to do with your electricity. This is the way we make measurements. You can literally put this lead anywhere in a circuit. If you got 2 meters, you can put this black lead at a completely different spot in a circuit. This is not circuit common. This is your common to your meter. On the oscilloscope, that black lead is ground. It is not common. It is ground. It's grounded. So if I was to take an ohm meter and measure between this little black lead right here, right there, to that center post on my outlet, you would measure pretty close to 0 ohms. This is grounded. So this is not a common. I mean, if I get into a circuit that is grounded, then this guy right here has got to go to ground. If I put it in a circuit that's not grounded, then I can put this anywhere in the circuit, but I can't use my other probe and put that ground another place in the circuit, right? Understand that? So that was why I was able to measure this AC a while ago, is because that transformer is ungrounded. It's an isolation. Your house is not. So your house, that center wire, that center tap is grounded, connected to earth ground. So there's my DC. Of course, what I want to do now, if I want to measure this, and of course this is going to give us P, is I would come over here and do what? I'm going to come over here and I'm going to shift it down. Notice, here's another thing I got to show you. Here's my reference, so I can tell that this is 0 right here. So we'll put it down on the bottom because there's no negative component. And then what I can do is I can make my scope more accurate. Makes sense? And then I would spread it out. I've got one cycle. Then I'm going to move it over to a line. I have it on 1 millisecond per division. So this is pretty neat. So each one of those would be, I'm expecting this to be 6.3 milliseconds. I'm sorry, 8.3, because it's 120 cycles, right? 1, 2, 3, 4, 5, 6, 7, 8.24. Which we thought it was going to be about 3. So your scope is not perfectly accurate because of the spacing between your divisions. So this is 120 hertz, right? That's a cycle, 8.3, so 8.3 milliseconds. If you just reciprocal that, it's going to give you 120. So we're inputting 60 cycles, so we're getting 120 out. Another thing that I need to make sure, let me I'll pop this down so I can do that. And we'll bring it back up so y'all can see it. Is my scope is basically taking pictures. And then my AC's over here doing this, and if they're not in sync with each other, then what you do is you come up here and you get something that looks like this. So what's happening is we want our scope and our signal to be in sync with each other. We call this trigger. And what we do is we trigger on a voltage and we trigger on an edge. So you don't need to trigger on DC, but this is pulsating. So over here, this is my menu right here. It says trigger, right? And I'm going to click on this. And then it comes up and gives me some options. It says, okay, I'm going to trigger on the edge. I'm going to trigger on channel 1. Okay. I'm going to trigger on the rising edge. And then that's all we need. Okay. So auto means if you don't trigger, it's going to generate one. If you have it on normal, if you don't trigger, your scope will be totally blind. So I'm going to turn this off. Now what this is, way up here, there's a white line. There's a little thing that says trigger. So look what's happened. I'm triggered on the positive edge, right? But my positive edge is not ever getting up that high. So since my positive edge is not getting up on that high, then my scope is not triggered. It's not synchronized. I'm going to come over and take this trigger adjust right here. You see the white line pop up there? Now watch what happens as soon as I get it in here. It did what? Froze, right? Here's my trigger point right here. This is a digital scope, so you can actually see. I don't know if you can see the little arrow right here. So let me move it. Let me move it over. So this is actually the trigger. Positive edge. If I come up and bring my little line, so it's crossing right here where the trigger's at. So that shows you where you're at, what you're actually triggering. A digital scope, if this was an analog scope, the trigger is always over here on the left. But this is a digital scope, so it's literally storing stuff all the time. So what's nice about this is it actually shows you what occurs before the trigger. Pre-trigger and after. And that's about it. If you get totally confused, you can't find something, then we have an auto trigger right here that we can come in. It's going to throw both channels up there, put them in the center. It's going to choose something for you, and then you can go from there. So that's pretty neat about a digital scope. An analog scope, you have to find it. So your screen's blank. It might be way up here at the top or way up down at the bottom. And you didn't know which direction, so you turn it. But this guy right here, it will find the signal for you. What's that button? That's that nice little blue button. Then I can come up and turn off channel 2 if I want to, if I'm not using 2 channels. And then there's my channel 1. Then I can start moving around, bring it down to the bottom. If you see this, it means your scope is tracing too slow. So that means you need to make the time for division less. That means you're going to turn this to the right. And notice it starts increasing, and that's where looks like we might be having a little problem with the trigger. Oh, that's out of trigger. Oh, let's see what it chose. Notice it's not triggered. So what I need to do? So we chose auto. So auto figures out which channel to trigger on. So we probably need to look at our trigger and notice it chose what channel. You go through that? No, it's channel 2. You probably get rid of it, channel 2. Channel 2 is turned off. So it's looking for the rising edge on channel 2. But channel 2 is not up there. So we'll just come over and hit this. And then go back to channel 1. And then it freezes. So if you turn this little knob right here, nothing happens. If you get it down into the waveform, odds are you're telling the scope to trigger on a channel that's not even there. So that, for some reason it chose channel, when you hit auto, it's gonna choose a channel for you, right? And you might be able to go back and do that. So those for vision. Don't play with these things up here. Don't get your run stop. Both for the vision. 2 channels. You can look at 2 channels. You can look at 2 things. Unfortunately, I got the full wave bridge. But on your halfway in your full wave center tap, since you got the same common, you can actually look at the input and the output. So we're not using, these are not really Scope Pros. Scope Pros are only about $30 a piece.